Hello everyone, I'm Sayantan and I will be talking about our recent work in which we investigated whether expressive posterior approximations can improve the performance of variational continual learning. Variational continual learning takes advantage of the fact that approximate Bayesian inference provides this very general framework for continual learning. So starting with a prior distribution over the parameters of a Bayesian neural network, that's PW, after learning task one, that's after seeing the dataset D1, what we end up with is the posterior distribution over W, that's the parameters given the first task. And when we move on to learning the second task, we can treat the posterior that's learned after task one as the prior for task two. And we have access to the dataset D2 for task two, and we can use these two things in order to learn the posterior distribution PW given D1 and D2. And we can continue in the same way for subsequent tasks. And at the end, what we will end up with is the posterior distribution over the parameters given all the tasks. Variational continual learning uses the mean field variational inference approach, where we consider this approximate distribution Q phi, which we assume to be a diagonal Gaussian distribution. And the ultimate aim is to make this approximate distribution as close as possible to the true posterior distribution. So one obvious thing that is evident here is that if the true posterior distribution is is very complex, it can have multiple modes, for example, then it might be very difficult for a simple diagonal Gaussian distribution to closely approximate the true posterior distribution. There are many alternatives to mean field VI, such as using mixture models or implicit distributions, but the focus of this talk will be normalizing flows. The basic idea of a normalizing flow is that it takes samples generated from a very simple distribution, mm, such as a Gaussian, as in this image here, and it converts it to a sample from a much more complex distribution by passing this data through a sequence of bijective functions. Variational inference has also been used together with normalizing flows, and it has been shown that for latent variable models such as variational autoencoders, this performs better than using the mean field approach for variational inference. But when we want to use normalizing flows with Bayesian neural networks, it's a little more complicated because the dimensionality of the parameters of a Bayesian neural network is very high. So the authors of the multiplicative normalizing flows paper get around this by using a sort of approximation for a normalizing flow. What they do is they start off with a vector z, which is of a much lower dimension than the network parameters, and they sample z0 from a Gaussian distribution. Then they pass this vector through a normalizing flow and obtain a sample z, which comes from a much more complex distribution. This vector z is then used as a mixing term in this conditional approximate distribution of the posterior, which ultimately is used to yield a sample of network parameters. So for a fully connected layer of a Bayesian neural network, this conditional distribution is given by this Gaussian, where zi is an element of the vector z here. In MNF, multiplicative normalizing flows, this is the evidence lower bound, the objective that is maximized. And we are particularly interested in this term shown in blue, which involves the use of the approximate posterior as well as the prior. And note that the approximate conditional posterior is given by this expression. So we note that we can rewrite the KL divergence between two normal distributions in this way. And then we use the fact that we can use the posterior distribution from the previous network as the prior in place of the prior for learning a given task, right? So what we do is we replace PW in this expression by Q phi of old, and then we rewrite uh, using the previous expression and end up with uh, an expression for the KL divergence that we use for training our network for continual learning. So to summarize, this shows the learnable parameters of one layer, both for mean field on the left and normalizing flows on the right. So we see that for normalizing flows, in addition to the mean and standard deviation parameters for the network weights, we also have additional parameters for the normalizing flow, as well as the mean and standard deviation parameters for the initial mixing terms at zero. We performed experiments using the permitted MNIST benchmark and used 10 tasks. We used a train validation test split of 50,000, 10,000, and 10,000, and we used networks with 3 hidden layers, uh, each of which had 200 units with ReLU activations. So this figure shows the mean test accuracy. So that means that suppose when a network is trained on task 4, it calculates, after being trained, it calculates the test accuracies on task 4, 3, 2, 1, and 0. So all tasks current and everything that came before it. So for 10 epochs, we see that mean field performs better than normalizing flows, but as we increase the number of training epochs, first of all, for 50, they are quite the same, but for 100, normalizing flows performs better. But we can also see that as we increase the number of epochs, the overall performance degrades. But this mean accuracy does not give us the whole picture. So for example, for 10 epochs, we can see here that um, the performance of both the kind of networks are dominated by the performance on the very first task that is learned. So it can be seen that for later tasks, the networks face a lot of problem in learning them, right? So the first task is remembered well, the later tasks are not remembered or not learned very well. But this trend reverses when we move on to 50 or 100 epochs. Uh, so for 50 and 100 epochs, we see that the older tasks are forgotten faster and the newer tasks are remembered quite well. When we look at the case for 100 epochs, we see that up to task for task 0, 1, and 2, the performance for both the mean field and the normalizing flows is quite similar. But for the later tasks, that's from task 3 onwards, there's quite a big gap in the performance of normalizing flows and mean field. So normalizing flows performs much better in remembering more recent tasks. So this this gives us an indication that normalizing flows may have this ability of uh, gracefully forgetting old tasks, and this might be a capability that is desirable in certain circumstances where it is not necessary to remember everything from the past as the network learns more and more tasks, right? So, given the kind of setup that we use here, we do not store any kind of sample data from the different data sets that the network encounters, nor do we have any kind of parameter growth. So we use a constant network capacity. And so if these are our constraints, then this thing might actually be a desirable quality. But to conclude, we see that in general, for permitted MNIST, the performance of mean field and normalizing flows is pretty comparable, but with more epochs, normalizing flows gets better than mean field. And there is also a slight indication of this graceful forgetting property. But we realize that a lot more investigation is needed in order to confirm this, and we will be conducting future experiments on complex data sets such as Core50 or CFAR. And we will also be looking at more complex at alternative VI techniques such as implicit variational inference. Thank you for your attention.